So my dear student friends, welcome back to my next lecture, that is a module number 13. And yesterday in the last class we were discussing about estimation of mass transfer coefficients and different theories, and one can use the film theory, penetration theory, surface renewal theory and surface structure theories. And we also studied about the boundary layers. We said there is a coefficient that we called as the eddy momentum diffusivity existing in the turbulent flow, which is same as momentum diffusivity in the laminar flow. The only difference is the eddy momentum diffusivity is property of the flow. It doesn't depend on the fluid properties, whereas a simple momentum diffusivity depends on the properties of the flow. And as we discussed, it is not possible to tabulate all the values of your eddy momentum diffusivity, eddy mass diffusivity or eddy thermal diffusivity. And that is the reason we are using different theories. Then we also learned about how to estimate the mass transfer coefficients experimentally, and we said we have a experimental setup like a wetted wall tower where the gas is flowing down, from bottom to the top, and the liquid is coming from the top to bottom. Then there is a contact between the gas phase and the liquid phase, so the liquid may be evaporating into the gas phase. So one can measure how much of liquid that is transferred or from the liquid phase to the gas phase, and from which one can estimate what is the mass transfer coefficients. Now we know it is not possible, as I told you already, for the estimation of mass transfer coefficients for all possible conditions. We have several of the experimental conditions. Maybe your Reynolds number may be ranging from 1 to thousands and thousands. So it is not possible for us to estimate the mass transfer coefficient at all possible conditions, and that is the reason what we can do, we can have some sort of analogies between the heat transfer, mass transfer and momentum transfer, and these analyses will help us to know the mass transfer coefficient by knowing the knowledge of your heat transfer process or the mass transfer process, momentum transfer process. So as you know already, there are some analogies which are existing in the laminar flow, and one of the things that we know, we can use the Newton's law, that is tau is equal to minus mu into dV by dz, du by dz, maybe dux by dz. And when you talk about the heat flux, maybe we can write k into dt by dz, and when you talk about mass flux J, that can be written as dAb into dCA by dz. And this can be reorganized. Maybe what we said is nu, a kinematic viscosity, dux into rho divided by dz, just dividing rho and multiplying rho. This can be written as dividing with rho Cp, that is nothing but k by rho Cp is nothing but alpha thermal diffusivity into d rho Cp by dz, and this is same as dAb into dCA by dz. When you look at these three equations, this equation is applicable for the momentum transfer, this equation applicable for the heat transfer, this equation applicable for the mass transfer operation. And if you see here, we have a momentum flux, here we have a heat flux, we have a mass flux, and here we have a momentum gradient and we have a energy gradient here. The T into rho into Cp is nothing but energy. Energy is the gradient for the heat transfer to occurs. Concentration or maybe a chemical potential is the gradient for the mass transfer operation. And we can see there is a coefficient what we called as a kinematic viscosity, or what we can call it as a momentum diffusivity here, that is nothing but a proportionality constant between the momentum gradient and the momentum flux. And here we have a thermal diffusivity, which is the proportionality constant between the heat flux and the energy gradient. And here also we have a mass flux and the concentration gradient and the proportionality constant, we said mass diffusivity. So this is thermal momentum diffusivity, this is the thermal diffusivity, and this is the mass diffusivity, each one having a units of meter square per second. Now, that is what we can see. There is so much of analogy is existing between these three equations. So we have the coefficient multiplied by the some sort of a driving force that gives you momentum flux, maybe heat flux, and the mass flux. And at the same time, if one can look at nu and alpha and DAB, there is a slight difference in these three. This nu and alpha are the property of a single fluid. Property of a single fluid. For example, when you say water is my substance, and one can say what is the kinematic viscosity or the momentum diffusivity for the water at a given temperature and pressure. But when you talk about alpha, thermal diffusivity, this is also a property of a substance. Maybe if I say my substance is the stainless steel, and what is the K, what is the rho, and what is the Cp, I know, and I know what is the value of thermal diffusivity. But whereas when it comes to the mass transfer operation, you have a proportionality constant. This proportionality constant is not a property of one fluid, it is a property of the two fluids. That means here we have the substance A is flowing through the B. This is what one difference is there between the mass transfer operation, heat transfer operation, and what do you call it as your momentum transfer. Then the second thing is we have your heat flux. This momentum flux is a tensor, and this heat flux is the vector, and here mass flux is also a vector. So that means tensor means we have tau xx, we have tau yx, we have tau zx, and we have tau xy, and we have tau yy, and we have tau zy, and here we have tau, what do you call it, x z, and we have tau y z, and we have tau z z, and these three are called as the normal stresses, and the remaining thing we call it as a tangential stresses. Whereas when it comes to the heat flux, we have only x direction heat flux, y direction heat flux, and z direction heat flux. Similarly, when you talk about the mass flux, we have Jx, that is the mass flux in the x direction, maybe mass flux in the y direction, mass flux in the z direction. This is another difference that one can see. This tau xx means we applied the momentum, or the flow is taking place in the x direction, and what is the momentum, what is the shear stress in the same direction, that we call it as the tau xx. And here the tau yx means there is a flow in the x direction that is transformed into the y direction. That is a momentum is transformed into the y direction, that we call it as a tau yx. And similarly we call it as a tau zx, where we applied the fluid flow, or the fluid is flowing in the x direction, and it is creating some momentum in the z direction. So that is what we call it as a tau zx. So similarly the other things can be explained here. So what we can say, the momentum flux is the tensor, whereas the heat flux and the mass flux are the vectors. So there are some similarities that are existing between the three different fluxes, what is existing in the three transfer phenomena. And so maybe if one can understand the how to estimate this value, maybe one can understand how to estimate this value. Similarly, one can understand the how to estimate this value. So what I want to tell you, there are some similarities existing between the one flow to the other flow, and that is what we call it as a lamina. That is what we call it as an analogy, and this is applicable only for the turbulent flow. Similarly, when you talk about the turbulent flow, so similar sort of analogies are existing between the your E nu. Similar sort of analogies are existing between the E nu and E h and E m, E d. So, and when you look at this, this is what we told yesterday. maybe in some cases u nu is equal to EH is equal to ED, that is when Schmidt number is equal to Prandtl number, that is equal to 1, your u nu is equal to EH and that is equal to ED. And if any value of Schmidt number greater than 1 and a Prandtl number greater than 1, so there we are going to have some sort of a similarity, UH by u nu, that is equal to ED by E nu. So what we concluded in the in the last class, what we said is, if I know eddy moment and diffusivity, I can estimate the eddy heat thermal diffusivity, or I can estimate the eddy mass diffusivity, or maybe one can equate this to E nu and E nu, that is nothing but EH is equal to ED. That means if I know the eddy thermal diffusivity, one can find out the eddy mass diffusivity. So what I want to tell you, there are some analogies existing also in the turbulent flow, but the thing is estimations of and it is not easy to mathematically represent this is very difficult. So there are several analogies proposed by different people to understand their relationships or their similarities. Right now, one of the analogy, that is nothing but a Reynolds analogy. So the name itself indicates it is proposed by the Reynolds, and what he has assumed, the turbulent diffusivities, the turbulent diffusivities, that is nothing but E nu, that is nothing but EH, ED are equal. Then the second thing what he has assumed, the molecular diffusivities nu, alpha, DAB are negligible compared to the eddy momentum diffusivities. Eddy momentum diffusivities. Then the third thing what he has assumed, Prandtl number is equal to Schmidt number, that is equal to 1. Then fourth one, turbulent conditions are prevailing. These are the assumptions made by the Reynolds in his Reynolds analogy, and based on that he developed a correlation for the estimation. He developed a correlation to relate your momentum transfer process with the heat transfer process, or the momentum transfer process with the mass transfer process, or the heat transfer process with the mass transfer process. So now in the next section, what we are going to discuss, how to relate these two. As we know, yesterday we were discussing your tau is equal to sum of the due to molecular diffusion as well as eddy diffusion, du rho divided by dz, and similarly we written as q is equal to alpha Eh dt by dz. Then we have written mass flux Ja is equal to dAb Ed dCA by dz. These are the equations that we have written yesterday. And now, as for the now what we can do, we can try to establish the relationship between the momentum transfer process and the heat transfer process, and we can apply that in the case of Reynolds analogy. What he said, alpha nu and alpha are negligible, and EV is equal to EH. So that means this can be neglected, this can be neglected. Then what we can do, we can write EV is equal to tau d u rho by dz, and EH that is equal to q by d into t into rho into Cp divided by dz. And EV is equal to EH. So tau by du rho by dz is equal to q by dt rho Cp divided by dz. And now from this equation one can write tau by q into Cp dt is equal to, so this is the thing that we are writing here. Now we can do further simplification here. What one can say, we have tau by q. Suppose if you take any pipe and if you take any location, maybe this is the location we are going to take. Suppose heat transfer is occurring from wall to the bulk of the liquid, and the momentum transfer is also occurring from maybe wall to the bulk of the fluid, then what we can say, at a one particular point the tau by q is constant. This is the important thing what one can say. The tau is going to vary, the q is going to vary, but the tau by q is going to be constant. So tau by q is constant at a particular location. So what one can do, at a given r, maybe I can take this as some r, at a given r this can be integrated, because at a given r we know what is the temperature, at a given r what is the velocity you know, and tau by q is nothing, tau is varying, q is varying, but tau by q is more or less constant. So what one can do, so once if you know that r value, this can be integrated between the maybe boundary condition between r is equal to r0 to r is equal to r, and that is at t is equal to ti, that is nothing but at the wall that interface temperature is nothing but Ti, where velocity is equal to 0. At t is equal to some t, let's say any point in the section, your u is equal to maybe let's say u average. So at a given r, the tau will be varying, q will be varying, but tau by q is constant. Now as we said, t is equal to ti, u is equal to 0, t is equal to t at point, u is equal to e average. So what we can do, we can integrate this expression between these limits, and we can write it as u average minus 0 is equal to tau by q into Cp t minus ti. Further we know q is equal to h into t minus ti, and tau is equal to friction factor by 2 into rho u average square. Now we can substitute this value of q and tau in this expression. We can write u average is equal to f by 2 rho u average square divided by h into t minus ti into Cp into t minus ti, that is equal to f by 2 is equal to h divided by Cp u average, that is equal to h into h divided by Cpg, where G is nothing but a mass velocity, right? So what we are trying to do, we know the friction factor. From this friction factor one can estimate the heat transfer coefficient. This is what the important conclusion what one can draw from your Reynolds analogy. And similarly what one can do, we can also combining the equations of momentum flux and the mass flux, and it can be written as f by 2 is equal to f divided by c into u average r, that is also equal to f into k average, kc u average. So this is what one can write. So that means if you know the friction factor values, one can either estimate the mass transfer coefficient f, or one can estimate the mass transfer coefficient kc. So this is what we call it as the Reynolds analogy, and given by the Reynolds. And one of the major limitation, it is only applicable for the turbulent flow. And if flow is not at a fully turbulent flow, then this analogy is going to breaks down, and it is the molecular diffusion becomes important. So we cannot apply this analogy when the turbulent flow is not going to be existing. Then the next analogy is given by the Prandtl. In the case of Prandtl analogy, what he has done, he has taken separately about the molecular diffusion and Reynolds analogy equation for the turbulent flow. So molecular diffusion, regular molecular diffusion for viscous sublayer, and Reynolds analogy for turbulent region. So just what he done is, whatever the Reynolds analogy, in the case of Reynolds analogy, the molecular diffusions are assumed to be negligible. So now the Prandtl, what he has done, so he has taken the Reynolds analogy for the turbulent region and the regular molecular diffusion for the viscous sublayer. He clubbed these two things, and he has provided some sort of analogy, and that we call it the Prandtl analogy. Then we have another analogy, Van Karman analogy, and in the case of Van Karman analogy, so here Van Karman not only taking about the viscous sublayer and the turbulent flow, is also taken about the buffer zone, or what we call it the transition zone. So he has written these three he tried to club a Prandtl analogy along with the equations applicable for the turbulent zone. Then we have another analogy that we call it as a Chilton-Colburn analogy. So in the case of Chilton-Colburn analogy, this is the most important analogy that we use in the mass transfer operations. And what Chilton and Colburn has done, they have done series of experiments with a different different fluids. Maybe yesterday we are discussing about the wetted wall towers. The liquid is flowing down, gas is flowing up. So we can change fluids. That means instead of air, one can use maybe nitrogen. Maybe instead of nitrogen, one can use some sort of a helium, maybe argon, maybe hydrogen. So different sorts of a fluid, gas fluid can be used. And when you talk about the liquids, we can have a different liquids. Maybe water is the one liquid. Maybe we have ethanol, maybe methanol, and different liquids we can take. So what this Chilton-Colburn has done, they have done the series of experiments. They have done series of experiments by changing a different fluids, so that your Schmidt number is going to vary. And based on that, they have provided the analogy, and this analogy is the most successful analogy out of all the analogies. And based on that, they have provided some sort of a correlations, and those correlations we will discuss at length now in the next few minutes. So in the case of convective heat transfer process, as we know, convective heat transfer process, we know your Nusselt number is equal to 0.023 Reynolds to the power of 0.8 and Prandtl to the power of 0.33. This is the very famous equation that we call it the Dittus-Boelter equation, and where he said Nusselt number is equal to 0.023 Reynolds to the power of 0.8 and Prandtl to the power of 0.33. So this also can be written as Nusselt number divided by Reynolds number into Prandtl number, that is equal to 0.023 Reynolds to the power of 0.2 and Prandtl to the power of 0.67. And then this Nusselt number divided by Reynolds number into Prandtl number is called as a Stanton number for heat transfer, that already we have discussed in the last class. And this Stanton number for heat transfer, that is equal to 0.023 Reynolds to the power of minus 0.2 and Prandtl to the power of minus 67. And then this Stanton number heat transfer and the Prandtl number 0.67, bringing the Prandtl number on this side, this is nothing but 0.03 Reynolds to the power of 0.2, and this Stanton number into Prandtl to the power of 0.7 is called as the most important factor, is nothing but a JH factor. where JH factor is nothing but a Chilton-Colburn factor for the heat transfer process, and this is nothing but JH is equal to 0.023 Reynolds to the power of minus 0.2. Then further we know this is nothing but F by 2. This is nothing but F by 2. So we can write, so that means here one can take a JH, that is nothing but 0.023 Reynolds minus 0.2, or what when one can have, that is also equal to the friction factor by 2. So if you know the Reynolds number and one can calculate the friction factor, one can calculate the JH value. If one once knows about the JH value, we know the Stanton number, we know the Nusselt number. So once if you know the Nusselt number, one can estimate the heat transfer coefficient. So this is the most important correlation that was given by the Chilton and Colburn, and they said it is a JH factor, that is a Chilton-Colburn factor. Similarly, one can write for the mass transfer operations, your JD, Chilton-Colburn factor for the mass transfer operation, is equal to 0.023 Reynolds to the power of minus 0.2, that is also equal to friction factor by 2. So similarly, what was the story that we told, the same story is going to be applicable here. So once if you know the Reynolds number, one can estimate the what do you call it as a Chilton-Colburn factor for mass transfer operation. So one can estimate the Sherwood number. So JD is equal to Sherwood divided by Reynolds into Prandtl number, and that is equal to Stanton number. This is equal to Stanton number for mass transfer into Schmidt number 2 by 3, that is equal to JD factor, where Stanton number for mass transfer operation is given by Sherwood number multiplied by Reynolds into Schmidt number. So what we did is we have kept the corresponding dimensionless numbers in place of heat transfer process for the mass transfer process, and we have written the Stanton number for the mass transfer operation. So then we are going to get the JD value. Once we are going to get the JD value, then one can estimate the mass transfer coefficients. So as we discussed, we know that I have some plots which is Reynolds number as a function of friction factor, maybe this sort of a plots we have. Similar to that, so we have a Reynolds number versus either JH or JD. So if I know simple Reynolds number, I can find out what is the JH or JD. So from that one can estimate the Stanton number. So one can estimate the either heat transfer coefficient or the mass transfer coefficient. And in the case of turbulent flow, as we discussed yesterday, even if Stanton number and Prandtl number are greater than 1, one can write your JH is equal to JD. That means your momentum diffusivity in the heat transfer process is same as is equal to momentum diffusivity in the mass transfer process. So one can write JH is equal to JD, and once if the JH is equal to JD, one can write your mass transfer coefficient F is equal to H into C, Cp into rho multiplied by Prandtl to the power of Prandtl divided by Sc to the power of 0.67. And we can solve one problem on this. Maybe at that time you can understand or appreciate the importance of these correlations. So here, as you know, this F is the mass transfer coefficient, H is the heat transfer coefficient, C is the concentration, Cp is the heat capacity, rho is the density, Prandtl, as you know, Schmidt number you know. So if I know the heat transfer coefficient, I can estimate the mass transfer coefficient. So that is the beauty of these correlations. So in addition to this, we have several of the analogies. As we told, as I told you, Sherwood and different people have done different experiments, and based on that, they have given several of the correlations, and by varying different liquids and different gases, and we have. So, just I can give you one example. Flow through the straight circular tube. Flow through straight circular tube. And when flow through the straight circular tube, your friction factor by 2 is equal to J, what do you call it, nu, that is equal to JH, that is equal to JD, and that is equal to 0.023 Reynolds to the power of minus 0.2, what we discussed now. And this is applicable, the Reynolds number between 10,000 to Reynolds number 10 lakhs. Similarly, plot flow across a flat plate there your J nu is equal to JH is equal to JD, that is equal to 0.037 Reynolds to the power of minus 0.2, and this is applicable between Reynolds number of 3 into 10 power 5 and 5 into 10 power 8. So what I want to tell you, if geometry is going to changes, the Reynolds number is going to changes. So we have one sort of a correlation, and these correlations, there are many correlations are given in the literature, and maybe if you look at any standard textbook on mass transfer operation, maybe of your tribal, maybe you have any other books, if you have, when we can look at these equations, you can find different types of correlations. And just to share some of my experiences with you, when we are studying our BTech third year chemical engineering, and when we saw these sort of correlations, and we did not understand the importance of these correlations, but today I can tell you with my experience, what are the correlations that are available in the literature may not be sufficient to solve the problems related to chemical engineering. And to tell you one example where I have done my PhD in the area per operation process, so my geometry is like this. I have a membrane here, and this is the geometry what I have used. My liquid is coming here from the top, maybe through a what do you call it, as a inverted funnel, and here it is flowing. The liquid is coming here through a inverted funnel, and it is spreading over the membrane, and it is going back. Now, right, depends on the Reynolds number. If I change the Reynolds number, your turbulence is going to be changed here. Once the turbulence is going to changes, your mass transfer coefficient is going to changes. If mass transfer coefficient is changes, even if you are going to use a simple film theory, your film thickness is going to changes. If film thickness is going to changes, your mass flux is going to changes. So what we need to have some sort of a correlation where one can estimate how to estimate the mass transfer coefficient for different flow conditions. And actually this is my small area of my PhD, whereas my PhD I have done different things. But the thing is, even today there are no correlations are available for the estimations of mass transfer coefficient for this type of flow geometries. So what I want to tell you, what are the correlations? Maybe when you look at this tribal textbook, there is a table number 3.1 is there. So there are several of the correlations are given, and these correlations may not be sufficient for some of the applications. So these correlations has to be developed continuously, and different people like Sherwood, maybe Linton, maybe some other people, they have developed different type of correlations for the estimations of mass transfer coefficients for different flow geometries and flow conditions. So, and that is what I want to tell you. Maybe in the exam, during your examination time also, you need not to remember all these equations. What people will do, they will give you, if this is the Reynolds number, this is the correlation you have to use. If this is the Reynolds number, this is the correlation you have to use. So the student has to understand what is my Reynolds number. Accordingly, I can the correlation is available for me for that geometry. Try to understand that geometry. So here I said a flat plate, here I said a circular tube. I cannot use this correlation if mass transfer, if the flow is taking place over the flat plate. Similarly, I cannot take this correlation for the estimations of mass transfer coefficient if it is a circular tube. So the student has to understand clearly for what geometry, flow geometry, these correlations are available, what are the Reynolds number where it is applicable. Accordingly, you have to select the correlation, and from which we have to estimate the mass transfer coefficient. Once mass transfer coefficient is estimated, the mass flux can be estimated. And there are several correlations that are given in the literature, depends on your Schmidt number as well as the Reynolds number. So maybe one can look at those correlations, and you need not to remember those equations. That's what I'm trying to tell you. So there is a standard literature is available. You can take that literature whenever you are interested to read, whenever you are interested to solve the problems related to that geometry, that flow conditions. So these are the various types of the correlations that are available, and the Prandtl has given in the Prandtl analogy what he has given that the Stanton number for heat transfer is equal to friction factor by 2 volt divided by 1 plus 5 square root of F by 2 Schmidt number, Stanton number for mass transfer, Schmidt number minus 1. And similarly, the same equation can be written as F by 2 1 plus 5 F by 2 Prandtl minus 1 for Stanton number for heat transfer process. So this is the correlation that is given in the Prandtl analogy, and if a Prandtl number is equal to Schmidt number, that is equal to 1, then this term SC is equal to 1, so this is going to become 0, and it's, simply your Stanton number for mass transfer is equal to Stanton number for the heat transfer, that is equal to section factor by 2. This is what nothing but a Reynolds analogy, right? And try to understand the beauty of these correlations, where the Prandtl has developed this expression, and when you say if Prandtl number is equal to Schmidt number, that is equal to 1, then the Prandtl analogy is becoming a Reynolds analogy, or maybe that is the Prandtl analogy is just an extension of a Reynolds analogy, where not only considering about the Prandtl, not only considering about turbulent flow, he has also considered about the molecular diffusions, and based on that he has developed this sort of a correlation. So this is another sort of a correlation that is available in the literature, but the thing is, I want to caution you one thing, and these correlations cannot be used whatever the way you like it. The thing is repeating again the same thing. If the correlation is given for the circular tubes, that correlation cannot be used for the flat plates. So, and if the correlation is given for some Reynolds number, you cannot use that correlation for some other Reynolds number. And if the correlation is given for the some Schmidt number and some Prandtl number, those correlation cannot be used for the other conditions. So, and what one has to discuss now, we have to discuss about the applicability of these analogies. And in this case, applicability of analogies, there are several things. As I told you, you have to remember the several things. One important thing is the flow conditions and the geometry must be the same. The flow conditions and geometry must be the same. Then that means this is what I told you. If I have a one correlation for the heat transfer process, where flow is taking place in a circular tube, and if you want to use that correlation for the mass transfer operation, this is only applicable when mass transfer is taking place through in a pipe. So if mass transfer is taking place over the flat plate, that correlation cannot be used for the estimation of mass transfer coefficient with the knowledge of the heat transfer coefficients. Similarly, during the development of the heat transfer correlations, it is assumed that no mass transfer is taking place during the development of heat transfer coefficient correlations, or what do you call it as a heat transfer coefficients correlations are developed, no mass transfer. And when you want to use the analogy for the mass transfer operation, we have to assume that no net mass transfer is taking place. Heat transfer coefficients correlations are developed with assuming that no mass transfer is taking place. So when somebody wants to use this sort of a correlation, there should not be any net mass transfer, no net mass transfer. So that means that is applicable only for the equimolar counter diffusion, Kc prime or Ky prime or maybe Kg prime. Do you understand or not? When the heat transfer coefficient correlations are developed with no mass transfer. So when you want to use these correlations for the mass transfer operations, what one has to do, these equations are only valid to predict the Kc prime, Ky prime and Kg prime. That means equimolar counter diffusion. There is no net mass transfer that is taking place. And we can also use Sherwood number is equal to FL into C by dAB, FL by C dAB. And this equation is applicable in the absence of a chemical reaction. Try to understand, if you want to apply these analogies, the flow conditions and geometry must be same, and this heat transfer coefficient correlations are developed with no mass transfer. So if you are using that correlation, and what we are going to get it, there should not be any net mass transfer. That means applicable only for the equimolar quantity fission. So that means we can only estimate the Kc prime, Ky prime and Kg prime. And when you talk about Sherwood number, that is equal to FL by C DAP, then this equation is applicable only when there is no chemical reaction. Then the third thing is the boundary conditions must be same. The boundary conditions must be same for both the both the process. That means in the previous example, when you take a falling liquid is there, this is the falling liquid, this is the gas. Now the gas is transferred from the gas phase into the falling liquid, and now when you want to use this correlation for the heat transfer operation, there should be heat transfer from the gas phase to the liquid phase. If the heat transfer is taking place from the liquid phase to the gas phase, one cannot use the correlation, right? That is heat transfer from the gas to the liquid, falling liquid film contacted with. So applicability of the correlation is valid only when heat transfer is taking place from gas phase to liquid phase. And then the second thing what we can say, during the derivation or during the development of the correlation, we said the wall is impervious to the permeation. That means this is a non-porous wall, no mass transfer is taking place through the wall. Similarly, when you talk about, when you want to apply this correlation for the heat transfer process, this is what we call it as a insulated material. The wall should be insulated so that no heat transfer is taking place. Then the third boundary condition, that is existing constant fluid properties. We have assumed that the fluid properties are constant fluid properties. So if you want to apply the correlation for the heat transfer process, one has to assume that the fluid properties are going to be constant. As we know, because in the case of heat transfer process, the heat is transferring, because of that the temperature is going to rises, and because of that the properties are going to changes. So when the properties are going to changes, obviously whatever the correlation that you are using, that will not give you good results. But thing is, in the absence of other correlations, we can use the correlation that we have developed for the mass transfer operations, and there one of the assumptions that we have made, it is nothing but a constant fluid properties. And the heat transfer process, if you see the mass transfer operation, here we have a interface. This is nothing but a y is equal to 0, and the mass transfer is taking place at the y is equal to 0. So if you want to apply for the heat transfer process, the heat is also transferring from the y is equal to 0. So heat transfer beginning at the same value, heat transfer beginning at the same value of y as similar to mass transfer, So these are the assumptions that one has to make for the applicability of analysis from one correlation to the other correlation. Then when you want to apply, we can apply safely. One can say your ED is equal to EH. This is the safe assumption. Maybe in most of the conditions, most of the situations, this assumption is valid. But at the same time, when you talk about E mu is equal to ED is equal to EH, this is not a safe assumption. This is only applicable when Prandtl number is equal to Schmidt number is equal to 1. And during this process, maybe there is another thing that comes into the picture. So we have we need to have a friction factor, and the thing is, we have two types of friction factor. We have a form friction and we have a skin friction. So we have to consider about only the skin friction and not about the form friction to apply the this correlations. Then generally it is said that it is better to avoid the moment and transfer correlations for the use in the mass transfer operations as well as the heat transfer process. So these correlations, whatever the correlation that we have developed for the heat transfer process, safely can be used for the mass transfer operations, but the correlation that we have developed for the moment and transfer process cannot be applied for the heat transfer process as well as the mass transfer process. So So generally it is safe to avoid the friction factor analogy for the mass transfer and heat transfer processes. So I think you are very clear about what is the importance of this analogies. Maybe that is where you can understand the applicability of one correlation to the other correlations. So in the next class, what we are going to do, we are going to solve some problems related to this mass transfer coefficients, and then we will understand the validity, applicability of these correlations for solving of mass transfer problems with the help of the heat transfer problems. Thank you very much.